Okay, can you see that okay? Is that right? All right. Up until this point, and you don't need to write this down, we have done the but the longer limit form of finding the derivative, which has been this limit as h approaches 0 of f of x plus h minus f of x all over h. So we've been doing that, and we obviously talked about when we were trying to find the derivative at a certain point. So in this diagram, we're going to try to find the derivative here. We initially called that x f of x, and then our other point was h units later, so it was called x plus h. And so that's how we arrived at that whole thing. So h was our distance between the points, and we were letting that distance approach 0. Now if you look at this diagram, the alternative form of the derivative is still going to be that whole concept, but we're not labeling the distance between the 2 points at all. We're just calling them two entirely different points. So the first point is c f of c, and that's the point we're going to be looking for the slope at. And the second point is x f of x. So we're still going to think about the slope between these 2 points being the slope of the secant, and that's what that is. That's your y2 minus y1 over x2 minus x1. That would be the slope of the secant when those points are separated. But we're going to kind of visualize and look at what happens as x slides closer and closer and closer to c. And so, therefore, we're not looking for the limit as anything approaches 0. We're looking for the limit as the x-coordinate approaches the c-coordinate. And when those 2 points are essentially on top of each other is when we kind of have the slope of the tangent line and therefore the slope of the curve. So it's the same exact concept, just a little bit of a different way of doing it. I will say that when we use this method, we're not going to so much get the derivative formula that we usually get with this one. Okay? This one gives us the derivative formula f prime of x that we can then use to find the slope at any given x value. When we use the alternative form, you're typically immediately and only interested in the slope at a known point right from the start. So we're not really going to get the equation for the derivative. We're going to get what the derivative value actually is at our c number. Okay? So if we jump to this first one here, and we're asked to use the alternative form of the derivative to find the derivative at 1, at a c value of 1. When we use this alternative form, we're immediately finding g prime of 1. And so I'm going to copy down this formula, just changing all of those c's to 1s. Okay? And actually, because this function is g of x, I'm going to use g of x instead of f of x. So it's going to be g of x minus g of c, which in this case is g of 1, divided by x minus your c of 1. Oh, I forgot to put my limit in there. Make sure you... Oh my gosh. I'm just going to put limit as x approaches 1 right in front of there. Okay, so I'm going to clean this up, and in for g of x goes the function. So in brackets, just to keep it organized, I'll do x times x minus 1. That's my g of x. Minus, 1 second, Sonny, minus g of 1. So I'm going to plug my 1 into there, and that's 1 times 1 minus 1, all over x minus 1. And then, like any limit, most limits I should say, when I go to plug 1 in right away, I will get the indeterminate case, so I have to simplify. So what happens to this? What does g of 1 end up being? What's 1 times 1 minus 1? 0. So that's nice. That section cancels. Not always, but here it does. And I'm left with x times x minus 1 over x minus 1. And in front, the limit as x approaches 1. And, Matt, what happens here? What can I do from here?
Cancel the x minus 1.
Yes, cancel the x minus 1. So I end up looking for the limit as x approaches 1 of just x, which is now an easy direct evaluation. Just plug 1 in, and I get 1. So g prime of 1 is 1. Sonny, what was your question?
What is the difference in terms of what you find at the end between this formula and the other formula?
So this formula, because I've actually been plugging in a c value of 1 the whole way, this is just giving me the value of the derivative specifically at 1. Versus before, when we were finding the limit,
at 1,
we were
equals 1?
At x equals 1.
Okay.
Yep. Before, when we were doing this, we were getting kind of a formula like f prime of x would equal 2x. You're not going to get an x in here anymore because x is approaching the number that you're looking for.
Okay.
So you're actually getting the value already.
Alright.
And this one is giving you, like, so if you ever needed to find the slope at multiple points within the same problem, this would be way better. But this is going to be a little bit, I think, easier
If it's at the specific
if you're only curious about a specific point. Exactly. Okay? So just to wrap our head around what the graph looks like and what we just calculated, obviously, you know, I like to show you this so you can have good context. Here's your image at 1, which is right about here. Your slope is 1, and we can confirm that it's a positive slope, and it's not all that steep if we were to draw a tangent line in there. So we just found the slope specifically at that point. Okay? Any questions? All right. So if we jump to the second one, which is an f of x rational graph, we're looking for a derivative at 3. So f prime of 3 is what we're looking for. I'm just following that formula from above. I'm changing all of my c's to 3. So limit as x approaches 3 for f of x minus f of c, which would be f of 3, over x minus 3. In for f of x just goes the function, 1 over x. What's f of 3 in this case? 1/3. All over x minus 3. And like most others, we're going to have to clean this up. So we have some complex fractions. Getting a common denominator in the numerator, that's going to make, I need a 3 and a 3 here, x and an x here. That's going to make my numerator 3 minus x over 3x. And actually right now I'll keep change. Instead of dividing by x minus 3, I'm going to multiply by the reciprocal. And Lizzie, what do you make from that? Good. Those cancel to make -1. So I'll just throw a negative in front of that. And so now I can evaluate my limit as x approaches 3 for -1 over 3x. And when I evaluate that, Emma, what will I get?
-1/9.
-1/9. So we just found out that the slope at 3 is -1/9. Okay? To the right of that, any questions on that? To the right of that, I asked a question, what would happen here if I was looking for f prime of 0? So we're going to do that. The process is going to be a little bit quicker, you'll see. So f prime of 0, now my c value is just 0. So it's going to be the limit as x approaches 0 of f of x minus f of 0 all over x minus 0. And f of x is still 1 over x. What's f of 0? Right, 1 over 0, which is undefined. So I'm immediately in a jam here because I can't really work that out. I can't get a I like to get rid of the complex fractions by getting rid of a common denominator. So immediately I can't even evaluate this at 0. Now looking at the graph of 1 over x, and by the way, if this limit can't be evaluated, then the limit does not exist. And if the limit does not exist, then the derivative at 0 or the slope at 0 cannot exist. So knowing what the graph of that looks like, you know, one of the many reasons why our derivative might not exist, why doesn't our derivative exist at 0? Right, because there's an asymptote there. The function doesn't even exist there. How can you say what the slope is on a graph when the graph doesn't even appear there? Okay? It clearly doesn't have a slope there because it doesn't even exist there. So one of the reasons we might see, and we've seen this visually already, but you now see how that it's going to mess with your calculation. One of the ways in which we'll find out that, oh, this function's not differentiable at 0. Okay? And just for the sake of looking a little more closely at it, we said that our slope at 3 was negative 1/9. And sure enough, if you look at over here at 3, we can all agree this is a negative slope. Yes? Still technically decreasing slightly forever. But again, it's slight, so that's why it's 1/9. Okay? All right. Next example, we have g of x, x plus 3 to the 1/3. So we're looking for g prime at negative 3. So that's going to be our limit as x approaches negative 3 of f of x minus f of negative 3 over x minus negative 3. So when you plug in f of x, you get x plus 3 to the 1/3. What is f of negative 3 going to be? Minus, what's f of negative 3? When I plug negative 3 in here, Amelia, what am I going to get? You don't know? Okay, if I plug, I guess it's technically g of negative 3. If I plug negative 3 in right here, you tell me, what's negative 3 plus 3? 0. 0 to the 1/3 power? 0. So when you're doing that f of, and I should have used g because it is a g function, g of negative 3 just means you're plugging negative 3 into the g function. Okay? And divide by x plus 3, which is nice because we can kind of lose that 0. So I still have the indeterminate case here if I plug in negative 3. What can I do to simplify this? Any ideas?
If you cancel out the x plus 3, it would be 1 over 3 minus 1.
You're on the right track. It's not that I can cancel out x plus 3, but I can use my exponent rules of common basis. So I don't cancel out x plus 3, but this technically has an exponent of 1. So a common base divided by a common base means you can subtract the exponent. So that's going to give me x plus 3. And what is 1/3 minus 1? Negative 2/3. Okay, well, if I plug in negative 3 now, I would get 0 to the negative 2/3 power, which, based on our negative exponent rule, that's the same as 1 over 0 to the 2/3 power, which is still undefined, right? So really, there's no way I can simplify this to make direct evaluation work. I get 1 divided by 0, I get an undefined, and that's because this limit of this function is undefined, does not exist. So because that limit does not exist, our derivative at negative 3 does not exist. So I'm going to show you this function, and it's going to be a different reason why we are not differentiable at negative 3, but when I show it to you, you should see it. So take a look at the g of x function, and look at what's happening at negative 3, and why do you think it's not differentiable here, meaning it doesn't have a slope there. Why does the slope not exist at -3?
Vertical line.
What'd you say?
It's a vertical line.
It's a vertical line, okay? It's like one of those cubic graphs, but it's like flipped sideways, so that when it does its little wiggle, it momentarily has a vertical slope right there. The tangent line right there is a vertical tangent line. Just to magnify it a little bit, it's doing this. So your tangent line at that point happens to be up and down. And the slope of a vertical line is undefined. So for that reason, we're not differentiable at -3. And again, it'll come up in your algebraic work. You'll see that it's not differentiable because your limit won't exist. But visually, I want to show you two reasons why that all kind of can come together. Because here you have a vertical tangent line. Okay? This one here, absolute value function, we're going to try to differentiate at 4. So f prime of 4 equals f of x minus f of 4 over x minus 4.
That's 1 point.
I'm not done yet. Sometimes I forget them and I go back and I squeeze them in.
That's still 1 point.
You're right. You're right, VBAC. You're right.
You did make that zero.
VBAC plus 1.
Plus 1 for what?
Never mind.
No, like,
If you didn't go to the bathroom to start every class, you might know the rules.
go in the middle.
Or the middle, even better. Or the middle. Alright, so our f of x is there. Minus, what's f of 4 going to be, Amelia? Can you do it this time? What's f of 4? 0. All over x minus 4. Okay, so that's nice. That 0 cancels. So we're left with the absolute value of x minus 4 over x minus 4, which should look familiar to you. What is the limit of that type of function?
Sometimes it doesn't exist.
Sometimes it doesn't exist. Sonny, what did you say?
Depends which side you're coming from.
Correct. It depends on which side we're coming from. This is our jump function parent graph shifted 4 units to the right. So to the left of 4, we're at -1, and to the right of 4, we're +1. So overall, what is the limit as we approach 4? Does not exist. So the original function, that just plain old absolute value function, for some reason, it's not differentiable at 4. We know why the limit doesn't exist for this type of function, but looking back at our original function, hopefully you all have a grasp on what an absolute value function looks like anyway, but just to get it concretely in front of you. We've talked about this briefly, but now we kind of see how algebraically it shows up as does not exist as well. Why is this not differentiable at 4? No, the slope's not 0. If the slope was 0 there, then f prime would equal 0. Then the slope would equal 0. The slope is not 0 there.
What's changing? What's the slope doing? It's going from negative to positive.
Okay, but going from a negative to a positive isn't necessarily the issue, because here's two cases. Here's one that goes from a negative to a positive, where our derivative does not exist there. Here's another situation where we're going from a negative to a positive, but the f prime does equal 0, like you just suggested. What's the problem with this one?
Not continuous. Well, the one is.
What's not continuous?
Right.
Both of these are continuous, right? Limit from the left, limit from the right, function value. Limit from the left, limit from the right, function value. The functions are continuous, but the slopes are not changing continuously. Meaning, this slope we'll just pretend is -1, and then it drastically changes to positive 1. Whereas this one might be negative 1, but then it's negative 0.9, negative 0.8, and it's this continuum that will lead it into 0, and then turn it into a positive, but gradually and continuously, versus the sharp corner, where we abruptly jump from a slope of negative 1 to a slope of positive 1. Does that make sense?
Yeah, that's what I was kinda trying to.
I know it was. I was helping you through it. I know what you were trying to say, but we gotta make sure we say it, you know? These Disney kids need to know what's going on. Alright, so this right here is a case where if you see a sharp corner point, then you will not be differentiable there. So we are not differentiable at sharp corners. I guess I don't even need to say sharp, I could just say at corners, but we'll say sharp just to really hit it home. Oops. Any questions? What I like about this is I could just show you pictures of, oh, sharp corners, we're not differentiable. Vertical lines, we're not differentiable. Where the graph doesn't exist, we're not differentiable. But what this does is it also shows you algebraically, if you're trying to find the derivative at a certain point, and what sorts of things can happen to let you know that that limit does not exist and therefore it's not differentiable from an algebraic perspective. Like, most of you, if you didn't have a graph and calculator and you weren't shown a picture, you're not going to know what that graph looks like. And because you don't know what that graph looks like, it's not going to be as easy as saying, oh, right, it's not going to exist because we go vertically quickly. You know, you're going to still have to do the algebraic work and arrive it does not exist because the limit's not going to exist. Okay? All right. On the back, though, we do get at that visual approach just for each of these graphs, looking for where it's not differentiable. So in part A, Allie, how you doing way over there? Everyone else came closer to join, and you decided that you were going to hang tight. Where is this not differentiable?
At -3 and 3.
Very good. And what is this a case of? Why is it not differentiable there? Because it comes to a point. Exactly. Good. And on B, Aaron, where is this not differentiable? -2 and 2. Very good. And why is it not differentiable? Right. Because there are asymptotes there, and the graph doesn't even exist at those numbers. And in part C, where is this not differentiable, Sonny?
Is it always differentiable?
No.
Then it's 0.
It's 0. Because here's the thing. You need to be continuous in order to even have a chance at being differentiable. Because your slope leading into a point has to be gradually coming as, and here we have a sharp jump. We've got a negative slope, negative slope, negative slope. And although it probably does hit 0 and then it comes out of 0 and then it's negative again, because you have a discontinuity there, being differentiable is out of the question. Okay? This is a sharp point. There's not a continuum there. Do you see what I'm saying? So anytime, if it's a short point within a continuous function, yes, that counts as a sharp point. We're not differentiable there. But also if it's at the end of a segment of a function, that's also considered a sharp point. Because remember, you have to be able to have a limit from the left and from the right. And you don't you don't in this case. So one key thing is, if a function is not continuous, at a point, then it's definitely not differentiable. So if it's not continuous, definitely not differentiable. However, I will say this, just because it is continuous does not mean it has to be differentiable either. Case in point, look back at A. This one's continuous, but that doesn't mean it's differentiable, right? It's continuous at -3, limit from the left, limit from the right, and function value at -3. But just because that is continuous does not mean it has to be differentiable. But this is the inverse. But if something is not continuous, then it is definitely not differentiable. Okay, can we wrap our head around that? So it kind of works one way, but not necessarily the other. All right. This example here. We want to try to find the derivative, the slope at 1. So we're going to look for f prime of 1. So we have the limit as x approaches 1 of f of x minus f of 1 over x minus 1. There's my f of x. Matt, what's f of 1?
0.
Good. Seems that it's often 0, but it's not always 0, which is probably an accurate statement. It is often 0, but not always. So this part is going to cancel. Direct evaluation, still no good. Any thoughts? I'm just going to erase this now, because that minus 0 we don't really need. Any thoughts as to what we can do to simplify this? Try to rationalize, good idea, because even if you factor, you're not going to be able to cancel anything because of that radical, because it'd be stuck under the radical. So if we try to rationalize to play around with this, the numerator is going to be 1 minus x squared. The denominator is going to be x minus 1 times radical 1 minus x squared.
I have a question.
Yes, Emma?
The numbers that you multiply by, is that supposed to be 1 plus x squared, or is it supposed to be 1 minus?
Nope. If I was trying to rationalize and get rid of a radical plus a different number, then I would multiply by the conjugate, the radical minus the different number. But this is just the radical. It's not a radical that's a part of a binomial. So once I'm here, now factoring and cancel may help. My numerator is just going to be 1 plus x, 1 minus x when I factor it. And my x minus 1, 1 minus x will cancel to make a negative 1. So I'm going to have negative 1, 1 plus x over the square root of 1 minus x squared. Now, here, when I directly evaluate, I still get, I'm better off, right? Because I'm not getting the indeterminate case anymore. If I plug in 1, I'm going to get negative 2 over 0, which does not exist.
It doesn't let me, you can keep going, it doesn't matter.
Right, well, it means we should take a closer look. Should we necessarily trust that? No. So what I'm going to do, and I kind of wrote it in the directions at the top, taking a closer look means think about what the graph will look like, which I'm not sure we all know exactly what that graph is going to look like, or take a look at the limit as you approach from the left and from the right. So, and just confirm that they're going to be different from each other. To confirm that that does not exist is hopefully correct. Okay? So if I go back to this and I look at my limit as I approach 1 from the right, if I plug in something slightly greater than 1, what's going to happen with 1 minus something slightly greater than it squared?
Is 2 too far away from 1?
Yes. Yeah. So if I'm plugging in something slightly greater than 1, like 1.1, what's going to happen when I do 1 minus 1.1 squared?
3.5.
Is it gonna be, is this, when I square it, gonna be slightly bigger than 1 or slightly less than 1? If I square 1.1, slightly bigger. 1.1 times 1.1 is gonna be slightly bigger than 1. So 1 minus something that's slightly bigger than it is gonna give me a negative. So it's gonna be the square root of a negative number over, when I plug in something slightly bigger than 1 in the denominator, that's gonna give me a positive, right? Regardless, that can't exist. So the limit coming from the right does not exist, which immediately confirms that this does not exist is true. But just for the sake of checking, I'm going to look for my limit as x approaches 1 from the left. If I approach 1 from the left, I'm going to get something slightly smaller than 1 when I square it. So 1 minus that number is going to be, you know, pretty close to 0, but at least a positive. I'll go with like 0.001 over, and again, if I plug in 1.001, slightly bigger than, oh no, I want to plug in something slightly smaller than it. So like negative 0.999. 0.999 minus 1 is going to be like a negative 0.001. So I'll get a limit coming from the left. But regardless, it's not going to match. And so this limit, we were right here, does not exist. Therefore, this function is not differentiable at 1. So f prime of 1 does not exist. Now, I'm going to look at actually a couple things here. Number one, I'm going to look at the initial function that we were trying to differentiate at 1. Look at what happens at 1. I'll zoom in. Why is it not differentiable at 1? What would you equate that to? Of the reasons we've seen so far. It actually, there is a point at 1, that's like a pixel error. I do have a point at 1. It's technically supposed to go down to 1, 0. Are you talking about the fact there's a little gap there?
Yeah.
That's a calculator issue. There is a point. It does go down to 1, 1, or 1, 0 rather. If you plug in 1, you'll get 0. Sunny?
There's nothing coming from the other side.
Right. There's nothing coming from the other side, so it's an endpoint. Okay? There's one, and then there's something else I think I could maybe claim. I think I could claim a vertical tangent. Okay? Once this is like the top half of a circle, right? So that's a vertical tangent at 1, which of course does not have a slope either. So I think it's actually maybe a little bit of both of those things playing into it, but regardless, you see algebraically why that was not differentiable there. Okay? The other thing I was going to show you, and I'm a little nervous I don't have time, so let me just move to the next example, and if I have time, I'll come back. Last example is a piecewise function. Okay, so if I'm going to try to find the derivative of this at 1, that's f prime of 1 equals the limit as x approaches 1 of f of x minus f of 1 all over x minus 1. And so when I jump to my next step, I immediately have an issue. What's my issue? Right, so which one would I pick for f of x? I don't know. Because, to be honest, when you're on the left side of 1, there's a function with one certain slope leading into 1. And when you're on the other side of 1, there's a different function that may have the same slope coming out on the other side, but it may also be different, because they're two different functions. So immediately I have to look at this as I come from the left, and then I'll, again, later on, look for this limit as we approach 1 from the right. So if I'm coming from the left, I'm using the top equation, which means f of x is going to be x, minus, what's f of 1 going to be? 1, over x minus 1. And that's a nice, easy simplifying before we go to evaluate. X minus 1 divided by x minus 1 is just 1. So what is my limit of 1? 1, right? My limit of any constant is the constant. So coming from the left, remember that's coming from the left, my limit is 1. The big question is this going to match when I come from the right? If it is going to match, the limit exists, and therefore it's differentiable. But if not, then the limit won't exist, and it won't be differentiable. So if I come from the right, I'm using piece number 2. So f of x is going to be x squared, minus f of 1 is going to be 1 squared, which is 1, all over x minus 1. I factor cancel, x plus 1, x minus 1. The x minus 1 and x minus 1 cancels. And so what's this limit now that I can evaluate and plug in a 1? 2. Good. So do they match? They do not match. So this overall limit does not exist. Which means, for some reason, this function is not differentiable at 1. Now it's a piecewise function, so to do it on my calculator is going to be a little bit of a challenge. I'm going to have to go up and draw a little bit on the board on top of it, because it's only going to give me both full functions. But the one to the left of 1, this is what we're following initially, and then we turn to the parabola right at 1. So if I kind of color over this, here's what's happening at 1. There's my point. So leading up to that, this is my graph. And then coming out of it, we're following the parabola. So is this function continuous? It is continuous. But why would it not be differentiable? We got that it wasn't differentiable. That limit didn't exist. Because it's coming to a tip. It's coming to a point. Your slope is 1, 1, 1, 1, 1, 1, 1. And then drastically, all of a sudden it jumps to apparently where we picked up on this parabola. Apparently where we picked up on this parabola, that has a tangent line of 2. So there was no continuation gradually moving it from a slope of 1 into a slope of 2. Do you follow? And it jumped, and therefore it's not differentiable at that point. Any questions on that? Does that make sense? Okay. And I just want to look back at that last function. Not the initial function, but the function that we were trying to find the limit of. We were trying to find the limit of this function. And we looked at it from the left and from the right. But no, I have no idea what that function looks like. Do you guys? Probably not, right? 1 minus x squared divided by x minus 1. And we were trying to find the limit as this approached 1. I couldn't decide if 1 was going to be an asymptote or not, because I really don't know, but it looks like it is, doesn't it? See how it's like going down towards 1? So we knew that coming from the right, what did we get here? Coming from the right, we got does not exist, and that was accurate, because the entire graph doesn't exist coming from the right. There is nothing there. But coming from the left, we got something. I just wasn't sure if it was going to be an infinity, and sure enough, it is a negative infinity. A positive divided by a negative is a negative infinity. So regardless, because the limit of this function didn't exist, our derivative didn't exist, and we already looked at that function to see why our derivative didn't exist. What's written there at the bottom, we already talked about up top. Your homework is just down there at the bottom.